In AR experiences, virtual contents are closely associated with the surrounding entities. However, it remains a challenge to create AR contents that can adapt to the spatial and context-dependent variations of different environments. We propose ScalAR, an integrated authoring tool that enables designers to create semantically adaptive AR experiences through immersive authoring in virtual reality. Now, we demonstrate the workflow of ScalAR by creating an AR cooking assistant. To provide a specific authoring topic, ScalAR collects physical scenes from potential AR consumers. An AR consumer collects the layout of the kitchen with 2 consecutive steps: plane detection and object detection. The consumer simply walks in the space and scans all the planes and objects of interest one by one. After the consumer finishes scanning, ScalAR generates the 3D layout using the collected data and visualizes it with 3D bounding boxes. The consumer can also adjust the size and position of the bounding boxes. Using the collected samples, ScalAR generates a large collection of virtual scenes that are highly relevant to the physical environments. Designers can easily travel across these scenes to design and adjust the AR experience. Now, a cooking expert starts to author the AR assistant using ScalAR. Beginning from the Edit mode, the designer can import AR contents such as this video display from the Asset menu. Now, the designer starts to define the semantic binding of the display. The designer creates a line connection to the countertop to define the identity level association of the display. Meanwhile, the designer creates an additional reference binding connection to further constrain this association. Then, the designer manipulates the display and adjusts its size to define the spatial association while referring to the surroundings. Now, the designer enters a traverse mode. Initially, our system applies the author's semantic binding to all the other scenes. So if satisfied with the AR content behavior, the designer can simply skip the scene, but our system will still record the scene as one demonstration. Now, in this scene, ScalAR provides a case where the countertop is much larger. The designer thinks the display should also match the size of the countertop. Here, the countertop that is closest to the range moves to the right of the range. The designer can also adjust the placement in this case. In the collected kitchen layouts, there are some small ones without countertops. For these scenes, the designer is informed of the absence of the countertop by ScalAR and redefines the semantic binding with respect to the range. The designer repeats the same process for a cooking menu and a timer. After the designer defines and adjusts the behavior of the AR contents, our system fits an adaptive model using the demonstrations recorder in all the virtual scenes. Now, back in AR, the consumer can either scan the physical scene or load a scan layout following the guidance. Then, ScalAR renders the AR experiences that adapt to the current scene with the help of the adaptive model. We demonstrate 2 application scenarios authored with ScalAR. ScalAR enables users with different areas of expertise to create AR experiences in the same VR environment. Here, 3 interior designers create AR interior decorations for the living room environments. The AR consumers can load all 3 designs, and our system accurately places the decorations according to the different layouts of the living room. ScalAR can also create interactive AR content while using the position of the AR consumer as a reference. The designer can create a user asset that represents the AR consumer's position. Using the same operations for other AR contents, the designer can also bind the user asset to the environment. ScalAR also supports the designer to create trigger behavior logic using line connections. For instance, the designer connects the position trigger of the user asset to a setup animation of the virtual dog. Similarly, the target of the animation can be bound to physical objects. Back in AR, the virtual dog will dynamically respond to the consumer when the consumer locates it in the designated position that adapts to different rooms. We conducted a 2-session user study to evaluate the performance of our system. In the first session, the users defined the semantic bindings of 6 AR assets in a virtual bedroom environment for us to evaluate the effectiveness of the adaptive model. In the second session, we evaluated the overall performance with an AR cooking tutorial. Thank you for watching. Please refer to our paper for more details.